Welcome to the Bytecode. I'm Hirosh Shafu, and today's episode is with Pia. Pia, thanks for taking the time.
Thank you.
Pia, Pia is a little nervous, but that's totally all right. Pia, why don't you briefly introduce yourself and introduce Herodotus?
Sure. So, my name is Pia. I'm a developer. I'm mostly doing the data processor and Herodotus, and I love Rust and open source. Um, so basically, like what we are mostly focusing on is trying to get the verifiable historical on-chain data, like leveraging the zk technologies. Um, and data processor is like one of the main product that we're like developing right now recently. Um, yeah, so let me maybe introduce data processor. Herodotus, like we've been trying to like solve the problem of basically um except for the like third party like or like RPC provider, there's not like easy way that you can like access the verifiable on-chain state. So that's why it's like a common like primitive around like storage proof. So we've been developing the um storage proof like products, something that we generate the storage proof like MPT proof and verify on the like smart contract directly. However, we feel like this is very expensive in terms of if you want to access some like large range of the slots, large range of the blocks, then you have to like generate the like proofs every time and then like verify every time as a like smart contract like transaction call, which is very inefficient. So what we've been developing like from early this year is a data processor, which is like using the zkVM. It's kind of like we are wrapping the coprocessor like design on top of the zkVM. So like normally if you think of a zkVM, you're writing a like arbitrary like program and you pass it to the zkVM. What does this zkVM do is like you generate some statement of the programs, so that means you could get the verifiable computation. But what we want to like add on top is we want to add the like verifiable on-chain historical state access as well. Like not only for the computation, we want to add the state access. The end state access in terms of not just like recent state access, like including very historical one, including from the Genesis block. So this is kind of like an overview, and like in technical details, I mentioned about zkVM. What we supporting is right now the Cairo VM, that using the Cairo like program as a arbitrary like program to pass it into the zkVM, the Cairo VM. And also like what I've been experimenting recently was a SP1, so we could do exactly same like exactly same data processing like logic on top of the Cairo VM like SP1. So like ideally we want to make this stack as a like modular like co-processing stack that kind of wraps around like multiple zkVMs as an option, so that people can choose whatever like their own needs plus like their situations match.
Yeah,
um
Pia, could you briefly explain what SP1 is?
yes, sure. The SP1 is basically one of the zkVM that using the Rust as a like program to pass it into the zkVM, so that you could verify the Rust RISC-0 based programs computations line by line, that you could generate the proof of this computation out of it. So like for the on-chain perspective, you could generate the like gross 16 or like Plonk proof, and then you could verify on the like EVM smart contract. So people can just write their like verifiable computation with the Rust and pass it to the SP1. So it's like a virtual machine for yeah. So yeah, I would define it as like that.
Okay,
um
sounds good.
yeah. So yeah, I think the like uh Where should I start? Oh, wait. So I think the good start next is we wanna basically support the verifiable on-chain data, and maybe I can briefly introduce like how this verifiable on-chain data like makes sense
Let's do
from
it.
the like storage perspective. Okay. Mm, yeah, sure. So normally like we could think of it as um like block cache. You could access the block cache with the block cache opcode with the latest like 256 blocks. However, like what we keep mentioning is like we want to access like more than 256. So we have a very huge accumulator that is exists in the on-chain smart contract, and um we are all the elements of this accumulator is verified block cache from the genesis block until the latest block, and we're like keep growing with it. So what does this mean is like from the latest block cache, we made a like zkVM program that is verifying the block cache of the that against the parent's block cache. So we pass the hash as an input, and then we verify it, and then we get the like verified data, and then we pass it into the historical like one like -1 like block. We calculate it and again, and we do it all the way back to the genesis block so that we could have a like verified by zkVM like block cache accumulator that exists on the on-chain. So like the idea of basically having the storage proof and we could able to access some verified on-chain state, it starts from here that we could trust the MMR root that is exist on the on-chain, and we are basically generating the inclusion proof on this accumulator, and we get the verified on block hash for certain block number. And then if we get a verified block hash, what it happens is like in the block, the header contains you could basically verify against the block hash that you retrieved just now, and you calculate the like block hash, hash it and match if it's correct. Then you could retrieve the state root, like receive root, like transaction root, whatever like root of the MPT, like state try. And then from here, you could verify the MPT proof of the elements that you want to get access to it, like account, storage, like transaction received, transaction, and all the like fields are available like regarding this logic. So basically, this is what it means by someone can actually access the verified on-chain state, like from the root of the block hash accumulator. Yeah, so this is the idea that we have in mind, that when we're trying to make a like data processor, we want to give the user to write some arbitrary like program, and then inside there they can define their own like logic of I want to access some account, I want to access some like header, I want to access some like transaction. I will show you the code of the how does the arbitrary program will looks like right after. But basically, when this program is running it, we have to get all the corresponding like inclusion proofs to kind of make this flow happen. So this is what data processor is like defined compared to the zkVM. Like zkVM is just you do the verifiable computation on some like public input. What we are doing, what we are wrapping it is we're preparing some inclusion proof so that like user don't need to basically care about like MMR verification, MPT verification while defining their logic. So yeah, this is like bit of a like a lot of things combined. So actually, I will like get through the code as well, like diagrams and codes. So maybe I can give you the example of how the program will look like. So if you see this program, this looks like a like normal Rust code. By the way, the repository that I'm right now referring is like AGP-SP1, which is like this data processor logic that using the SP1 as a prover backend. So in this case, the arbitrary program we're defining, that we are expecting user to define, is the Rust program. And actually, it is a SP1 program. But we wrapped with our AGP like main macro on top so that we could handle the pre-processing step. And what it means by pre-processing step is basically preparing the input of the zkVM program about the inclusion proofs that like that I just referred while explaining that how inclusion proofs are playing the role in terms of getting the verified on-chain data. Yeah, so if see the program, basically like you could define your own get header, get account, get storage, and as you can see, this is like a normal like Rust program. So you can just like add it, sum it, and even this whole like return value is like header defined by alloy like create. So you literally can just like use the struct very efficiently, and you write this program, and then what happened is like we have a like data processor client that is, as you can see, like abstracting the SP1 client. And then if you basically you can do the execute, prove, verify. I added this method because I wanted to use the prover network. So basically if you use this and you specify the program, like AGP program that you define with the macro, what has happened like underneath is like you first run the like online mode, and then you get the like memorizer like bean, which is basically memorizer is kind of like a like data structure, like data like struct that all the necessary inclusion proofs are defined. I can also like go through the struct right after. And then this, why we are basically need to return this file is because we want to use this value, inclusion proofs, as a public input for the zkVM program. And then after this is the SP1 SP1 client will generate the ELF file for the program that we pass. And then basically like after that we do the SP1 client proof, which basically have several options to generate the proof. And for this example that I maybe go through is like gross 16 proof, and then gross 16 proof you can verify an on-chain. So we have a like verifier contract that is also using the SP1 verifier as a interface inside. And then we first verify the zk proof. zk proof means like verify the proof that generated from the SP1, and then from that like number 5 implies that this program all the state and plus the computation is indeed correct. But what is missing is basically just now the explanation that I did. We are assuming that this root is correct. We do the MMR inclusion proof to get the correct block number hash, and from there we retrieve all the necessary data. So at the end of the day, like before we finish this like on-chain verification logic, we need to validate the integrity of the MMR root via the public value. What it means is like this program will commit the MMR related data, like Merkle Mountain Range related data that they had used while running this program. So this Merkle Mountain Range is the source of truth of this program to be indeed sound. So what it means is that after like 5 steps, like, okay, now the program is indeed correct. Like the inclusion proof makes sense. All the data that I defined, that user defined, is everything is valid. And then after 6, okay, now the source of truth exists in the on-chain smart contract. It matches. So now we can trust the whatever value that user returned from. So this is kind of like a sketch of how basically user can define their like arbitrary very simplified like logic in terms of accessing the data. For example, if you see this, like there are some keys that you can define your like block number. Even you can define the like chain ID, because this logic is fully happens in off-chain zkVM. So what it matter, like the chain IDs even doesn't matter. What it matter is like the root, like the root of the MMR. So what's very cool thing is you could define the like Ethereum Sepolia, like this header, and you get the value, and you could like in the next line you can get the chain ID from like Optimism or like Ethereum mainnet, whatever, and then you could like define the value, and then you can do like sum it up, like minus, like you can multiply, you can use the other like on-chain data like from it. This is kind of like a pretty nice abstraction that I wanted to share.
Here, maybe MMR is the Merkle Mountain Range, right?
Yeah.
What's the difference between a Merkle Mountain Range and a Merkle tree?
So there is a like very nice like blog post that we had, like exactly what is different with the Merkle tree and then Merkle Mountain.
Nice.
So if you can see this, basically this is how you expect about like Merkle tree. That you're computing the child and then get the parents, and then you hash it all the way up to the root, and then you have a only single root like per one Merkle tree. However, like Merkle Mountain Range is, we want to have a like various size of trees that like if you see this section, like if you treat it as a Merkle tree, we have like 3 Merkle trees. However, like in the Merkle Mountain Range, you can compute this. This looks like a node root, but we call it as a peak in the Merkle Mountain Range because we want to like compute like from here and treat it as a like whole like kind of like a mountain, not a tree, not a single tree. So this is kind of like a good way in terms of it is known data structure that is efficient in terms of inserting the elements. And the reason why we use this Merkle Mountain Range element, the data structure, is because like this is the only part that we are using the Merkle Mountain Range. And this section is about historical block hash accumulator, which means like literally like from the block 0 to like current latest Ethereum block number. We have to store plus update every single blocks. So that's why we choose to use this data structure for appending more easily.
Okay.
Yeah, and there's also like visualizer. Maybe this can help.
Oh, nice.
Yeah, so like if it's like just like what I mentioned, like normally this is like a tree, Merkle tree, but actually like if you see the virtual node, we treat this as a like one single like mountain, not a tree, so that you could like generate the inclusion proof for 1 to 27, 1 to 26, like not generating the inclusion proof from like 15 to like 1 to 12, and then like 22 to like 16 to like 20. Yeah, so it can contains like more larger range of the scope of element. Okay, so and also like we are keeping the Ketchuk tree and then Poseidon tree, like also like Stark Poseidon tree, and this is reasoning is because we have to use the based on the this data structure, we are growing on the on-chain smart contract, and each blockchain have a different like more friendly hash function. So for example, like in the EVM we use Ketchuk, and for the Starknet like we use the Stark Poseidon because it's like native field. So yeah, this is kind of cool, and I can also show you like get proof. So basically this is kind of like an inclusion proof, as you can imagine. Like you could basically like do it against the peak. Kind of looks like a Merkle tree, but it contains the like much like larger range, because you're like bagging the peaks, like this 15 to like 26. You're bagging the peaks to generate the root, single root out of it. Yeah. So is it okay.
Sounds good.
So
Sounds good.
thank you. Maybe, sorry.
No
Um,
worries.
one more thing that I can also share, like regarding this, because I mentioned about like how does the program looks like. Like SP1 case, we like share that. So SP1 case, let me show you like this. SP1 case, because the zkVM is like verifying with the RISC-V, like pretty much like a ROS program. So this is abstracting the SP1 program and use the and can able to use this type of like memorizer, which is like data processor can only support. Starting the case, we also doing the similar thing, like because Cairo VM accept the Cairo program, so this looks like a like normal Cairo like smart contract. However, this is not compatible with the Starknet. It's just compatible with the Cairo VM, and like this library, like EVM get header parents, like it also have like everything like just like this account storage like transaction like receipt, and this thing is in the behind. It abstracts the pre-processing step and then processing step. Like pre-processing step means generating the inclusion proof of the input of the zk program. Processing step is getting the inputs and just run it as a like normal zkVM program. So this is doing the same thing, and it has a like two-step, like two-phase abstraction. Yeah. So yeah. So it's kind of like this kind of concept I would like to explain, and I wanted to like share this one because it's kind of like a like fully made it with the ROS, and it's kind of like I started very like 1 month or 2 months ago. It's quite experimental, but it's like really nice experiment. Like it really nice like components in terms of like every abstraction, like including the SDK is fully written in Rust. So maybe I can like, if it's okay, I can jump on this code base in detail.
Yeah, for sure, for sure.
Okay, sounds good. Yeah, sure. Let me explain from here. So recap about the end-to-end flow. We write some program abstracts in the background. We have to run two steps. One is generating the input. Second is just running the normal zk program, and then we verify. And this two like second step and third step is basically how does this implemented is conditional compilation, which is in SP1. You can have a two different type of mode based on the target OS. Like normally, you're running on zkVM target OS if you do the cargo proof run. However, you can just treat this like Rust program, because it is anyway like Rust program. You could just treat this program as a like unconstrained mode, which it calls as a online mode. And the benefit for this is like you can get a STD and asynchronous IO like allowed, because like maybe near future it might be different, but like right now the STD plus like asynchronous like crates are not allowed on the zkVM mode of the program. And we kind of use this conditional compilation to like first doing this like second step, generating the inclusion proofs from the online mode. Like we first determine what kind of data that is needed, and then we fetch all the inclusion proofs and the state that is needed, and then we return as a like memorizer like file. And the second, and we basically, this client is doing this for us basically, but we put this file as an input file of the like zkVM mode compilation. It's actually like same program. That is pretty cool. Cool concept. It's just literally same program. Depends on like what target OS that you're compiling on. It do the different thing. So, and then we get the public input from here, and then we do the MMR MPT inclusion proof verification that like I just mentioned like earlier on, and then mark the data is verified, and then like commit the MMR metadata, and then like generate the ELF file, and then it goes like 4, 5, 6. Okay, so so how does this macro looks like? Maybe first, let's take a look at it. Is like as you can see that our concept is we get the multiple like historical like origin chain data mixed computation program somehow from the user, and then we deliver this data to the on-chain in verifiable way. So we have a like one chain ID to be specified so that it determines like which chain that we want to verify it on. And then as you can see, like this is how you write the conditional compilation, that about like if the target OS is zkVM mode, you do this. So this is a read function that I abstracted on the macro, that doing the two different behavior of if it's zkVM mode or if it's like online mode, not like unconstrained mode, it behaves differently, even though it's like the same code. So for example, like if you like read this line, basically if you use this line, and when you're like compile into the online mode, like even though this is like just AGP dash read, during the online mode it behaves like this. During the zkVM mode it behaves like this. And this type of idea is used for like every single stuff that we are kind of like designed. So for example, like commit also same, to like basically online mode there should be no commit logic. And the zkVM mode, we are committing the public value that we want to get access in on-chain later. But online mode, we are just saving as a like memorizer file, which is the second step that I just mentioned, like pre-processing step that I just mentioned about like generating the input file of the zkVM program. So if you have any kind of questions or like confusion, like please let me know.
I will.
Yeah. Please like interrupt me, please. Yeah, I'm just kind of unsure if I like explaining things correctly. Explaining things like in easier term. Okay. So I just mentioned about conditional compilation. So this part is pretty interesting. That if you see this, this is the part that user just see. User just define the key, and they use the memorizer and use some like exposed method that looks very intuitive. Like you just identify value that you want to get, and you get the value. Simple. But what is happening under behind is if you see this like leap memorizer, this is kind of like a core like core program, like SP1 programs that we are handling. Like for example, all the memorizer, we have a trait of the data that we can get. However, we define this trait in totally different behavior on online mode and zkVM mode. So the purpose for the online mode, the aka the pre-processing step, is we want to generate all the necessary data that we want to fetch all the necessary inclusion proof plus the data that user want to access, right? So for example, let's say the user mentioned, hey, I want to get account data. To make sure this account data to be valid, we first need to fetch the header actually. Because account verification is depend on the header. This is the flow of here. Account like verification, the root exists in the header. So from the account key, we can retrieve what kind of dependent header key that we need to get, and then we first get the header, and then later we get the account, and then this part is like just saving to the memorizer. Memorizer as in like the proof plus the data. And also because it's a zkVM. Oh, I forgot to explain that how does the memorizer looks like. Maybe this is not intuitive if I didn't. Okay, so memorizer is the main main structure that connects between the online mode and the zkVM mode. Because memorizer is the output of the online mode. Memorizer is the input of the zkVM mode as a public value. So it contains all the data that is necessary to make the verification logic sound. So we contains the MMR, of course, the source of truth, and then we have the maps, the cache map of all the keys and the values that we need to basically verify everything. And this key and values are obviously the things that we are supporting. Like for example, header account, beacon header, storage transaction, receipt. And as you can see, we contain the data plus the inclusion proof. Everything it contains the data and the inclusion proof. Beacon chain is different because we don't do the verification with the state MPT proof. It's we use the SSZ, but it's a different story. So, and okay, so basically, if we finish this line, we have a header plus Merkle Mountain Range proof, account plus Merkle Patricia Tree proof, and we save these values into the map. And there's some tricks that kind of prevents if it's already cached, we just skip it. If it's not, we fetch. And we do the same thing for account, receipt, like storage, like transaction, is about like we first get the dependent header, we fetch it, and save it. Storage case, because the storage case we use the zkProof RPC call, so zkProof is already returning the account. So in this case, we fetch the header, and plus we save the account like in the same fetch call. Yeah. So TLDR, what I just explained is I'm keep explaining about what is happening behind the abstraction. Like what is happening behind the abstraction is we have to do the two-step. Like first is online mode, aka like pre-processing mode. Second is zkVM mode. And during the online mode, we fetch everything that's necessary, just like the thing that I shared on the provider side. Yes. And then this interface is, as you can see, like memorizer get account. So this is connected to the program that user is writing. Memorizer get account, get header. So when the client, like when the client struct basically first accept this file, they will first run the online mode. And what the behavior is defined is basically this online mode. So this is how we're handling the two different behaviors. So now we fetch everything that we need. Let's assume like we fetch everything that we need based on the memorizer logic that I shared. And what happened is we get like now the memorizer struct is keep like mutated, like means like keep inserted the values that we want. And then now we can save this file. Now we need to basically connect the two different steps. And how we connect is we serialize as the bin code using the bin code crate, and then we serialize this memorizer like struct as a memorizer bin file, and then we save it in the root. And then this client will basically okay, and then the first step of the online mode is finished. Let me also get through this in the SDK perspective. So the client, the data processor client, first need to run the online mode. And then after this, step 1 is done. Now you get like bin code serialized memorizer on the root. And then the second step is running as a zkVM mode. This zkVM mode purpose is to generate the ELF file. And what it happens, again, we are doing the same thing. We are doing the different step, different conditional compilation with the same program. So we still have a like key and header memorizer, but if we go to this, like revisit this file structure again, now we need to basically compile as a zkVM. So what it happens is instead of like fetching those kind of stuff, we first verify the relevant data. For example, hey, I want to get the account. Then what we need to do is we first need to make sure that is the header that this account is rely on is indeed sound. We have to check this one first. And then second one is we retrieve the state root from the header. That is, we know that this is valid. And then this is kind of also like small trick that I don't want to like verify like 2 times, like same thing. So we keep the flag on it. And basically if we want to like verify the account, then we do the like MPT verification. I make it as a like separate file for the MMR and MPT verification logic itself. So this is how it works. And we do the same thing, like this logic is same as like adjust samely as like account, receive, storage, transaction. you have to first verify the header, and then if the header is verified, you do the original one. Wait, I clicked the header, so it's confusing. So you first do the header, and then you get the root, and then you verify the MPT against it. Like storage exactly same. Actually this one is like you have to get the header, you have to do the account also, and then you have to like get the storage root from the account, and then you verify the MPT against it. As you can notice, like basically this, like if the situation is like mainly about I want to verify the storage MPT, then I just use the method directly so that I don't need to like repeat the code. So like if you want to verify the storage, then you jump to the account, and if you want to verify the storage, you also like jump to the header, like something like this. And the header part is basically verifying the MMR proof that I just mentioned earlier on, the header accumulator, the Merkle Mountain Range. So this is so generally the explanation right now that I went through is about how to ensure the soundness, that is verifying against the header, and after this header is verified, like we verify the child, like I mean the dependent components against the roots for everything, like MMR, MPT, and then we repeat this step. Like we repeat the step all the way across. Like we handle everything that user defined from the get something method of the memorizer. So TLDR, just now the step that I mentioned is basically about how this program get compiled, like how this program get behave during the zkVM mode, which is like actual like the trace generation part. So okay, so maybe just like quickly jump again. Basically, like I first said, we run the online mode, and then second, we run the zkVM mode, and then this will generate the ELF file, which you can see here. Okay, now we got the ELF file, and then this is like client that is like wrapping on top of the SP1 client. So you could just use it like this abstraction, and you pass the AGP like program. And this proof, we do the two-step of online mode, zkVM mode, and then we get the proof, vkey as well, and then we verify. And I wanted to share this one because like this one.
Yeah, Pia, one question here. One question. How long does it take to generate the proof?
So this is the number, the clock cycle. So actually, like time may be tricky because the clock cycle, it depends on the machine. So clock cycle can be like best metrics for this, but I can like run it right now for the purpose of see how much if this takes. So right now the program that I write is header account storage. So you could see the trace as well. Let me run it. I need to get the private key, but it's not my private key is like SP1 private key. Maybe if yeah, I was testing this like today, so I didn't fix the EMV yet, but yeah, okay. So this is what it do is about network proof, that using the SP1 network, you will see how it looks like basically. Let me show you the trace. So I printed this because I wanted to like debug with the on-chain like MMR. later on the Foundry test. And okay, so first, what we do is we do the online mode. So if you see this, like execute, and yeah, this step is already abstracted the part of memorizer, like getting the memorizer. This serialized like file contains all the inclusion proof, and then this part is now running the zkVM mode, and this is the trace that I like wrote it down, like mmr mpt. Like I just need 3 because like I don't like the logic that I made is like I don't want to duplicate stuff, so I just do 3 verification. And as you can see, the time takes like this in my M2 machine, and the cycle is like this. And then right now I'm generating the proof not locally. If you yeah, so on the prover network, and because I want to generate the gross 16 proof, and gross 16 proof based on what they mentioned on the documentation, it requires like more than quite a lot of memory like spec is needed. So it seems like my machine is not doable. So yeah, the logic that I wrote is we wait until the proof get finalized. It takes like 2 minutes, based on what I tested before. So yeah, after this proof pass, I can share like the on-chain verification part as well. It takes like 2 minutes, so yeah, I mean, okay, actually I can share the contract slightly. The value that I will return with the return to the on-chain is basically this one. Like I return this 3 value because the step number 6, the this one. I need to validate the integrity of MMR root via retrieved public value. I need to validate the integrity of the MMR via the public value that returned from the SP1 proof. So basically, if I verify from here, okay, so what I pass is public value, and then the proof bytes, and this is the interface of the SP1 like verifier, and then like we verify the proof, and then this returns the public value that I wanted to return. And so this 69 to 70 means that SP1 proof is indeed valid. And then 72 to 73 is we're using the aggregator, and this aggregator is the Herodotus aggregator contract, which is this one, the contract that is growing this tree at Merkle Mountain Range. And then we kind of check that the root that we retrieved from the SP1 proof, if it's like correct with the aggregator contract that we are growing, the root, and then if it's valid, then return the result bytes. I put the arbitrary like result bytes, like so that people can like utilize on the on-chain. If not, it's just invalid. Yes. So okay. So basically, we did an online mode. Memorizer got saved to here. And then we did a like zkVM mode. We first compile the SP1 program, and we run the prover. Here's some trace, and then in this case we ask the prover network to generate the gross 16 proof from us, and we waited, and then finally like it got fulfilled, and then I got some basically what I got is this one fixture. So this is a small detail for the test. So basically, I just like return the value like as a this path. I get it from the like SP1 test template. So this is how like turn this gross 16 proof value as a format of Foundry task can parse it. And now I got some V key and public value bytes and then the proof from the SP1. And the test is just load it and verify it and then see if it's valid. Yeah, maybe I should do it. Yeah. Yeah, so basically like this state is the like on-chain Merkle Mountain Range state. And I mentioned that we growing the 2 hash function depends on the what kind of blockchain is more friendly of. So like Ketchup, Poseidon, and this is a test, so like this value is kind of like put it like I don't care about the Poseidon in this case because SP1 like we are verifying this SP1 proof on the Ethereum like chain, so we only care about the Ketchup. And yeah, this is the parsed from the gross 16 fixture, and at the end we check this is indeed the same as the root from the on-chain. We make sure that the source of truth is indeed correct, and the console log this last value is I console log the result, the bytes, and this bytes is come from here, and this V is basically a header. This Ethereum Sepolia, this block header, this is the block hash. So yeah, we can check if it's yeah, basically this is the result that we returned from the zkVM program to the on-chain.
Nice.
Yeah, I think this is yeah, do you have more questions? Oh, maybe this is a one one more like quickly introduce what kind of example that you could think of or like some variants. I was working on the small example regarding this, like how maybe this AGPSP1 like program can like run inside the XX. So yeah, if you see this, I define so the idea in here is like, what if we run the SP1 program every time the block got minted, like block got generated? And what if we pass the latest chain related data that is like that we can retrieve right after the execution hook as an input of this like program either? So basically, if you can see this line, like this chain committed is the notification that like when new block got like come out, and we get these two value, block number and the transaction length, and I just wanted to try like pass this value inside the SP1 like AGP SP1 program, and then by using this like abstracted client, I could just prove and verify, and this 16 to 34 will execute it every time the XX hook got executed. So this is also the test for like having a mock function with it. Yeah, so actually this, as you can see, this takes quite a lots of programs compilation and different type of compilation. So maybe like running inside the local environment everything fully would be bit inefficient. So that's why like I was thinking of this proofs that we could literally just use the network proof that I just showed like just before, and then we use this like proof network prover network. Yeah, and basically we do exactly same flow with the Cairo VM. But this one like the project scale is like lots like way more larger because it started
Mm.
like from this year. So yeah, just like just 3 sentence TLDR is like in here this CLI is generating the preprocessor, like the input file of the program. So and then so something like this. If you go through here, this is like kind of like a input file for the Cairo program that is verifying the like MMR MPT inclusion proof. And we pass this whole file and then we run the Cairo VM. And this is considered as a zkVM mode that I just explained on here. And then we send to the prover service, and then we verify on the on-chain. In this case, like Stark proof, verify on the Stark verification, Stark verifier that is deployed on the Starknet in this case. And then we also like validate the integrity of the MMR root.
Yeah.
Yeah.
Is it still compiling? Because I can hear the fans on your MacBook. Your MacBook is suffering right now.
Yeah,
Yeah,
it
it
is
is.
something. It's like
Okay.
yeah, it has a lot of dependency. As you can see, like it's like it's from the Plonky tree and all the resting, because like right now, as you can see, I'm trying to like showcase the rest. So uh the dependencies are pretty huge.
Okay. Yeah, and Pia, this is experimental right now. Also, what's the timeline on making this production ready?
Uh, so basically, the AGP, the Cairo side, is already on the production that user
Mm.
can just call the um user can wait, um uh okay, it's basically like user can just call the um like program that I just showed as the Cairo program, and then like they can do the local development. They can uh call the server that is already deployed, so you don't need to handle all of these like steps on your own. um so we can say this is like on production. SP1 is very experimental right now, because
Mm.
and ideally we would like to like merge this into two so that we can like get a flag on like just what kind of proving backend that you want to use as a enumeration, and then people can just choose the SP1 Cairo VM, and then under the line how this like flow goes is like all we are handling. um so SP1, like we are targeting to like making production. uh we'll probably like do the demos or like a workshop of the AGP in general, like during the DevCon. And yeah.
Mm. Nice. Awesome, Pia. Then, yeah, thank you for that great presentation.
um yeah, so uh, is it finished or like
No, no, we're still recording. We're still recording. I'm gonna put the repositories in the description down below. The blog post as well. The docs. Anything else you want to add?
uh like the basically I think uh, this and the documentation would be pretty nice.
Hmm.
Like so this is the like experimental repo that doesn't contain in the docs, and then the documentation is like explaining what does AGP is like generally doing. So so maybe this too can very nice explanation for the things that I explained.
Awesome.
Yeah.
All right, then, yeah, thank you very much, Pia, for this great presentation. Thanks, guys, for tuning in, and I'll see you on the next one. Bye-bye.